All right, so we've been talking about sort of coordination compounds, complex ions. We talked about, again, sort of coordination number, ligands. Remember, as we talked about, that there are certain ligands that do attach in sort of more than one place. Um, there's ones that are bidentate, which means they attach in two places per molecule. There's some that are polydentate. For example, we saw one that binds three places per molecule. EDTA binds six places per molecule. Remember, if it's able to sort of bind more than one place per molecule in terms of the ligand, it will give you sort of a, 2 for 1 in terms of the coordination number. So again, when we had an ethyl endyl diamine, um, if you have one of those guys, it will give you kind of like a coordination number 2 because they will bind twice per molecule. So as we talked about, it's not always sort of the little number that's sort of next to the ligands in terms of what the coordination number is. It does really depend on whether or not they're monodentate, bidentate, and or polydentate. We got into sort of the nomenclature of really coordination compounds and complex ions, and also sort of writing the formulas. Um, so remember, we sort of treat complex ions and coordination compounds, almost actually coordination compounds, really more like ionic compounds. There's a positive part and there's a negative part. And just like sort of when you name an ionic compound, positive guy always comes first, followed by the negative guy. And same thing with coordination compounds, positive guy, followed by the negative guy, both in the name and in the formula as well. We also talked about that. Basically, you could have any combination of those things. So we can have a complex ion that's positive. We could have a counter ion, which is there to balance out the charge that's negative, or vice versa. You could start with the counter ion and have the complex ion being a negative guy. We typically can find our complex ion a lot of times in formulas in the brackets. Not always, but a lot of times they are kind of put in these little brackets. And there's some rules as to how we kind of name these guys. A couple of them are we do name the ligands that are attached sort of in alphabetical order, regardless of the prefix. Um, and then the metal always comes at the end of the complex ion name, so are part of the name. So remember that again, if your complex ion part is positive, the metal part will come at the end of that first part of the name. If your complex ion is negative, the metal part will come at the second part of the name. Also, whether or not your complex ion is positive or negative, it's important in terms of how you name the metal. If your complex ion is positive, then you just use sort of the regular name you're probably used to for the metal, like iron, copper, and so forth. You also always put a Roman numeral for the charge. And again, even on things that we normally don't sort of use a Roman numeral for, we do typically in these sort of coordination compounds or complex ion naming. Um, the Roman numeral, just like normal, is basically the charge, the positive charge on the metal. If your complex ion is negative, you kind of go with the older school way of naming the metal, and you basically put an ATE at the end of it. So iron is ferrate, copper is cuprate, cobaltate, and all those kind of sort of names for those negative ions. Also, again, still put the Roman numeral there um, to indicate the charge. Any questions on that stuff that we talked about last time? All right, so I think where we left off was right here. Got a couple of ones we want to write the formula. So just to kind of finish up this little topic in terms of nomenclature and that type of stuff, take a moment or two here, and you want to come up with the correct formula for these coordination compounds. Is when we look at the name that we see the platinum 2 here. It comes at the end of the name. And that basically indicates that obviously what came before that should be the complex ion part. Remember that the metal with the Roman numeral will always come at the end of the complex ion part of the name. So we know that's the complex ion. We know that then this would be our counter ion that's happening here because of that. So we really just want to kind of dissect the name here. So triamine. Amine is NH3. Tri means there's 3 of them. So that kind of takes care of that part. Bromol is Br minus, and there's just one of those. And platinum 2 is a platinum with a +2 charge. So if we put this together, we end up with a PT NH3 3Br. So it's important to try to figure out, maybe what the charge is on this so that we know when we put our counter ion, which is chloride, sort of how many do we need in this particular case. So if we just kind of add up everything we got going on, that's +2, that's 0, that's -1, which means this overall complex ion really has a +1 charge. So that would tell us that we really only need one of these guys to balance it out. And that means that our coordination compound would look something like this with our 1Cl there to balance out the charge. Any questions on that particular one there? All right, so kind of working through the same sort of approach. First, we see cobaltate. We see Roman numeral 3 here. So this tells us this is the complex ion part. This means that over here, this is going to be our counter ion. So we'll work with the complex ion part first here. So hexafluoral is basically 6 fluorines. And that's it. Then we have cobalt that has a +3 charge, which means really our sort of complex ion is COF6. The overall charge of this guy, cobalt is +3, fluorines -1, and there's 6 of them, gives you a -6, which means overall this sort of complex ion part is using having a -3 charge. And again, that's important to know because we then know that we need not 1 potassium to balance it out, but we actually need 3 potassiums to balance it out. And that would give us a K3COF6. Any questions on those two there?
I have a quick question about
Yeah.
the first one. So,
Yeah.
if there were, since chloride is the counter ion, if there were 2 chloride ions, would it be considered dichloride or would it still be called chloride?
So is your question like, if the counter ion was like this, like that was the counter ion, you had 2 of them? Is that your
Yeah,
question?
if there was 2 or like 3 or 4 of them.
Yeah. So in terms of the counter ion, if you're asking about in terms of the naming part of it, in terms of the counter ion, you just pretty much name it whatever it is, regardless of how many there are. So kind of like, I guess we may have talked about last time, if you have something like CaCl2, this would be calcium and just chloride, even though there's 2 Cls there. So it's kind of named very much like that. So again, regardless if you have 2, 3, or 4 of these sort of chlorides, which are the counter ion, you would just call it chloride.
Okay, thank you.
And kind of the same thing as you can see on B as well here, even though there's 3 potassiums, it has no effect on sort of the counter ion name. So the counter ion name is pretty much just the name of it. So it'd be like the metal name, the front part, the whole name, regardless of how many you have. And then on the back part, even if you had a polyatomic ion as a counter ion, again, you would just use the name of the polyatomic ion, like nitrate, even though there might be 2 or 3 of them. Other questions? Okay. So that wraps up sort of our naming part of our coordination compounds and complex ions. So now we're going to talk about isomers and sort of the relationship to these really complex ions and so forth. Isomers are basically guys that have the sort of same molecular formula, but some type of different arrangement. So if things are isomers, what they basically mean is they basically contain the exact same number of elements and everything like that, but they do have some different sort of arrangements, maybe how they're connected, how they're put together in 3-dimensional space. And because there's those differences in sort of a lot of times connectivity, their orientation in 3-dimensional spaces, a lot of time isomers will have sort of different properties from each other. because of that different arrangement, even though at the core they contain basically the same sort of elements and all that kind of stuff. But there is some type of difference that occurs there. There's some different classes of isomers we're going to talk about here. There are structure isomers, which basically have different bonds, and there's coordination isomers and linkage isomers in that example. There's also stereoisomers, which have the same bonds, but sort of that different arrangement in three-dimensional space. That gives us some cis or trans geometric isomers and some optical isomers. We're going to talk about each of these here in just a second as we go through them. So why don't we start with the first type of isomers we're going to talk about, which are coordination isomers. And coordination isomers pretty much are guys that have the exact same numbers of everything. So if you just kind of count up everything that's going on there's one chromium in each of them, there's 5 NH3s, there's one sulfate and one bromide, so they have exactly the same. The difference though is in this case, in this coordination isomer, is what is part of the complex ion and which ones are not part of the complex ion. So remember that this is our complex ion part here. And if we kind of look at it, NH3 is 0, sulfate's -2, and bromine is -1. That means oxidation state here on chromium is +3. And in this particular arrangement, what we have in terms of the complex ion part is we got that chromium attached to the 5 ammonias. And also attached to the sulfate. And this makes up pretty much the complex ion part that has an overall charge of +1, actually. In this case, though, the Br is the counter ion, which means he's kind of hanging out here to balance out the charge, basically, between these two guys. Now, the difference between, say, that one and the one down here is when we look at the complex ion part. In this complex ion, there is no sulfate that's part of it. Sulfate actually is the counter ion in this case. And when we look at sort of the charge here, -1 and our -2, this is still +3. In this particular case, we have the chromium attached to the 5 NH3s. And like I said before, we actually now have the bromine that's part of it. And when we look at the overall charge here, +3 for the chromium, -1 for the bromine, this now has a +2 charge, this complex ion, with the sulfate there being the counter ion to balance out this charge. So although they have exact same numbers of everybody that's present, they actually yield two different complex ions. Both which have chromium in the middle, but actually both have some different overall charges. And that's what a coordination isomer is, sort of different bonds that are happening here. So in one case, the sulfate is part of the complex ion. In the other case, obviously it is not. Any questions on that there? These two complex ions probably would have some different properties. Again, one has sulfate in there, one has bromine. They also have different charges. So, they'll have a different effect. Another type of isomer was referred to as a linkage isomer. And much like the name sort of implies, it's sort of how the ligand is linked in to the complex ion. What atom on the actual nitrogen is doing that. So if we look at NO2 minus here, and if we sort of draw it here, look something like this. And like a double bond action happening there. And in this particular case, the nitrogen and also the nitrogen and also this oxygen, which is really what the minus is, they both have the ability to sort of bind to the metal. And they're not going to both do it together or at the same time. But in one case, what we see here is this is our NO2 minus ligand binding in. It's actually binding via the nitrogen there, the lone pair on the nitrogen. While if we look at the NO2 minus down here, it is binding in through the oxygen in this case. So a linkage isomer happens when you have the ligand having the ability really to sort of bind or link into the metal through a different element. And again, they're not going to both do it together in this particular case, but in one case, the nitrogen will do it. In one case, the oxygen will do it. Obviously, giving us some different sort of properties as well, because in one case, obviously, we now have a cobalt sort of oxygen bond, cobalt nitrogen bond. But overall, everybody else is pretty much the same. It's just sort of that way it links in, hence the name linkage isomer in terms of that particular ligand. Any questions on linkage isomers? Another sort of group of isomers are stereoisomers, and this is where we come across cis and trans isomers. In sort of organic chemistry, you see a lot of cis and trans isomers, and it usually revolves in organic chemistry around sort of a double bond situation. And basically, cis means same side. So when we talk about organic chemistry, it means that these guys are on the same side of the double bond. But basically, cis means that the groups are sort of at the same side. And trans is opposite sides, for example. So trans is opposite. And in the case of organic chemistry or sort of those double bonds, that means that they're on the opposite side of double bonds. In the case of sort of complex ions, they're sort of on opposite sides of the plane of the molecule is typically what we're talking about, while cis typically means that they're sort of on the same side of the plane of the molecule. So let's take a look at a couple of examples here. This is the cis isomer A of our PT NH32Cl. And our trans isomer there are pretty much the same guy. So again, having the exact same formula, just some different arrangements. And here, you know, if you look at the CLs, for example, the CLs are kind of on the same side of the plane of the molecule here. In this sort of square planar. While if we look at the CLs, they're sort of on opposite sides of sort of the plane of the molecule here. In this coordination number of 4 in this case. And these two guys, basically exactly the same formula. As you can see, nothing is different in terms of anything in terms of connectivity. It's just sort of their arrangement in three-dimensional space. And you can see this different arrangement does give some different properties. This guy will be more of a yellow guy. This guy kind of more of a pale yellow type color. Again, playing a little bit with some of the properties of these guys. Here's guys where we have kind of a coordination number of 6, which is octahedral arrangement. And the first guy here is our trans. And here, if you sort of think about this as sort of the plane here of the molecule, you can kind of see the CL is above it, and this CL is below the plane of the molecule. And again, that basically is trans of each other, those guys, opposite sides. Here again, looking at this again, if you want sort of like the plane here of the molecule, this guy's up and this guy's sort of on the same side of the plane of the molecule, which would be cis in this particular case here. So that's usually sort of the arrangement that you kind of see in a coordination number of 6 sort of deal, where we got kind of above and below that kind of center plane. While cis, you'll have above or below and somebody on the plane, meaning that they're on the same side. Now, optical isomers are isomers that have an opposite effect on plane polarized light. basically means that they can kind of move plain polarized light one way. It basically goes through a filter as it gets the light gets shine on it. Molecules that have non-superimposable mirror images are what are referred to as being chiral. And what does that mean? As we'll see in a bit, that basically means, for example, if you take your hand, you put it to the mirror image that you see is your other hand basically staring back at you. And if you pull out the mirror image of your hands, you can arrange those, move them around as much as you like. You'll never get them to sit perfectly on top of each other. And by sitting perfectly on top of each other, that means everybody's still arranged in the same orientation. This is not sitting on top of each other perfectly the same, because one's palm up, one's palm down, so it doesn't match. If you kind of flip them both palm up, the thumbs are on the wrong side. So there's no way you could rotate your hand image there from the mirror to get it to be perfectly everybody in the right orientation and fit perfectly on top of each other. And that's what's known as chiral total molecules, or those guys that have those non-superimposable mirror images. Things that are referred to as being achiral are guys that do have superimposable mirror images. These isomers are sometimes referred to as enantiomers, as we'll talk about. But here's some polarized light again. We have our light source, unpolarized, kind of go through a polarizing filter, giving our sort of wavelength in both directions. And if you do this sort of through a particular sample, it can kind of rotate that light by a particular angle that's called theta. We're not going to get into any sort of calculations involving that or anything like that. But it has that ability basically to do that, these type of isomers. There's our hand example there of things that are chiral. Again, if you pull out the mirror image, you're going to have some issues. Again, kind of palm up, palm down, and palm up there. Not going to fit on top of each other. Although you can get the thumbs to line up, you're wrong in that orientation. Again, if you flip it around, your thumbs will be on the wrong side and things really will not sort of flicks together correctly. So let's take a look at a couple of things here. We have isomer 1 and isomer 2. There are mirror images. The image of 1 is identical to 2. That cannot be superimposed. So there's no way that 1 can be turned in space to be the same as isomer 2. And it's sometimes really hard to visualize sort of what that all means, because if you look at it kind of quickly, you might be saying to yourself, it kind of looks the same. I don't understand why it doesn't. And it's really a sort of a slight difference. So as these things sort of reflect, this is the original image here, into the mirror, they kind of reflect there. He reflects backwards. He reflects, and we get to all this reflection that occurs. And when this reflection occurs, we actually end up getting a slight difference in where the bonds are happening. So, and it's really this guy to this guy bond right here. Those two nitrogen bonds get kind of moved around when it gets reflected to kind of in the back. So when we pull out that mirror image, this nitrogen bond is no longer sort of bonded, if you will, to the front nitrogen, and now makes really a connection to that back nitrogen, which means although it may appear like it's looking pretty much the same, every time you sort of rotate it or try to get it to fit, you're going to have that bond that's sort of skipping that front nitrogen, and they're never going to really line up correctly. And that's why sometimes it's really hard to visualize some of these things, but that's that slight difference that occurs as that thing gets reflected into the mirror. You get sort of a different bond that's sort of happening between those sort of guys. And again, it's going to just create everything being just off a little bit. You might be able to get some things to sort of line up, but other things will not line up correctly. Excuse me. Here's the trans isomer and its mirror image, and they are identical. They're superimposable, which means they're more achiral, and that's what we see over here. Again, as this thing gets reflected, guy gets reflected, he gets reflected to the front, he gets reflected to the back. Because of that, there's still that same connection that occurs as they get reflected. He gets reflected, he gets reflected to the back. Again, still having that same connection. And pretty much when you pull it out, it pretty much will sit perfectly on top of each other. Again, here, much like the other one, as we do that sort of reflection, reflection, reflection back, these guys are going to be the same. But here with the Cl is going to get reflected to the front. This nitrogen with the connection will now get reflected, you know, towards the back there. And that's going to create that different sort of bond in sort of the three-dimensional area there from where it is here. And again, we're going to get that area where it's not going to fit perfectly on top of each other there in our sort of cis isomer of our cobalt, and its mirror images are not superimposable. So they are going to be a pair of optical isomers. So chiral molecules that are non-superimposable will be optical and be able to move that sort of plane polarized light. Any questions on that there? So when two molecules that are mirror images of each other that cannot be superimposable, those are also what are referred to as being enantiomers. A lot of biomolecules are chiral, and some drugs are as well, but only one sort of isomer is actually effective in curing, for example, a disease. And that just goes to show you that, you know, although they are made up of exact same sort of molecules, and in the case here, kind of the same bonds, the difference in that sort of spatial arrangement of everybody in three-dimensional space does give things sort of different properties as well. Any questions on isomers there? We're now going to talk about sort of bonding in really complex ions and sort of, you know, where the electrons are and where they end up sort of when we start adding ligands in and stuff like that. So the formation of hybrid orbitals to share electrons, you might be familiar with hybrid orbitals, things like sp, sp3, you know, those type of things where we mix those atomic orbitals, right, to form these hybrid orbitals. The idea behind that is, you know, the idea of sort of same shape of molecules, same energy, makes for better bonding rather than trying to put together an atomic orbital, which is atomic orbitals are your sps and ds and fs, putting together an s orbital, which is basically spherical, with a p orbital, sort of a figure 8 teardrop sort of situation. They don't work very well together. So, excuse me for 1 second here. Okay, sorry about that. So when we think about sort of complex ions, as we talked about before, you know, with the sort of sharing of electrons in our ligands, we could kind of think of it more as a Lewis acid and base situation that's occurring, and donating and accepting those sort of electrons to the d orbitals. Electrons is where they're going to go. The hybrid orbitals are used by metals, depend on the number of ligands that are attached, and there's sort of a coordination to the coordination number and the ligands and sort of the geometry that we see here. For example, this is really sp3 d2, and really if we just count it up, that's 1, 3 more is 4, and 2 more is 6. This is typically where we see a coordination number of 6 happening here. The cobalt here going to accept electrons here from these 6 NH3s and make that complex ion, attaching there with our 6 nitrogens to come in there in a coordination number of 6. Again, kind of like hybridization with that sp3d2. These are some common sort of geometries that we see with complex ions. Tetrahedral, which is sp3. This is also square planar, which, if you remember, comes from really the expanded octet when you did sort of Lewis structures and stuff like that. And that's our sp3d2 as well. And linear, which is basically 2, which is our sp sort of hybridization that occurs with these complex ions. So there is sort of a relationship between coordination number and sort of the geometry that we see happening here. Again, coordination number of 2 going to give us linear. You could kind of think about it like electron pairs. Basically, 2 electron pairs, 2 bonds is linear when you did like Lewis structures. Tetrahedral is a coordination number of 4, which is 4 electron pairs and 4 bonds. Square planar, which is sort of that expanded octet, also has only 4 bonds and basically 6 electron pairs, which is why it's sp3d2. And octahedral, basically 6 electron pairs to that geometry there as well. So what we're going to talk about right now is sort of the bonding that's going to occur there in our d orbitals when we have, or where the electrons are going to be spaced out in our d orbitals for our metals in complex ions. Now, these are our 5 different d orbitals here. So coming over here and there, these are our 5 different d orbitals. And obviously, those are the shapes of them. And in the absence of any ligand that's present, we have these 5 d orbitals, basically all the same energy level, which means we would have our 5 d orbitals, and this would be the d orbital for the metal that's in the center of the complex ion. And because they're all basically the same energy with no ligands attached, we would expect electrons when they go in basically to fill up like normal, one at a time, right? And come back and kind of pair off. When we actually add some ligands, as we will see, we'll get some separation of these d orbitals. You know, maybe we'll get some separation where some d orbitals are higher in energy than others. And that's going to affect how these electrons basically come into the orbitals. They may get here and decide, well, those d orbitals are way too high. I'd rather just come and kind of pair up down here first and then come up there. They may decide, well, that's not too far up there. I'll just go in like normal. So there's this sort of splitting that we're going to talk about that occurs, how the d orbitals electrons basically get fitted into those d orbitals based on the ligands that are present. So let's take a look at this. This is what is referred to as the splitting that occurs, and it's sometimes referred to as crystal field splitting. And crystal field splitting is the splitting that occurs between the 5 d orbitals in the metal that's part of the complex ion. Again, in the isolated transition metal by itself, we got all these d orbitals that are, again, equal in energy, and it would have their d electrons populated like normal. With this splitting that occurs, as I just mentioned before, they may decide, well, again, not a big deal. This doesn't look so high. We'll go this way first and then come back. Alternative to that, they may decide the opposite, like I just showed you there, that they're going to go, no, thank you. I'd rather just come and pair off here. What makes that difference is this crystal field splitting, which is this difference in energy, basically, between these guys, and sometimes abbreviated with that little delta symbol. We could calculate that by taking E equals H times the frequency, H being Planck's constant. That's the frequency, usually in reciprocal seconds. And that ties into hc over the wavelength, where c is the speed of light. And obviously, that is the wavelength in meters. And that's because the speed of light is equal to the wavelength times the frequency. I throw back to some old equations here. And this also is sometimes just abbreviated with that delta. So if it basically has a very large sort of splitting that occurs, what we typically will see is a lot more paired spin happening. Remember that paired spin basically means in a orbital represented by the box, the electrons need to go in opposite directions, having the spin quantum number of +1/2, which would be that guy, and the spin quantum number of -1/2, which would be that guy. No two electrons in the same orbital, right, could have the same spin or the same 4 quantum numbers, and that's because they would have the same spin and they always pair up. So in the case where we have a really large crystal field splitting, we end up getting a lot more paired electrons. In the case where we have a very small sort of crystal field splitting, we end up getting a lot more unpaired electrons, basically, because they will go in sort of like normal one at a time, and we get these a lot more unpaired electrons that occur. How can we follow some of this stuff? Well, as I mentioned before, a lot of times we can use absorbance values, and we talked about the idea when we do absorbance values, we always want to pick the wavelength of maximum absorbance, which would be at the top of the sort of heel there. And when we do that, we'll get that sort of population of electrons that can kind of go upward. And again, this is actually where you can calculate the energy of those splitting of those fields, those d orbitals. So let's take a look at one here. And I think it's filled in for you. So we'll just sort of talk about it here, how we get to all that, and a couple of important things as well. So the absorption maximum of a complex ion is 470 nanometers. And that is obviously where we'd want to set our wavelength, as that would give us the maximum absorbance. Why do we want to set it at that maximum absorbance? I think we've talked about it before, but just a reminder, obviously, if you don't set it at the maximum absorbance, when you go run your samples, pretty much most of them will not pretty much be on scale. Because if you set it, for example, looking at that picture we were just seeing, if you decided I'm going to set my absorbance value at like 7 something, that's pretty much all the absorbance you're going to get, which probably means most of your samples would be off the scale. So what color is the complex ion, and what is the crystal field splitting in kilojoules per mole? The other important thing that I think we probably talked about as well is the idea that the color of like the solution that we see is actually complementary to the color that is being absorbed, or the wavelength that's being absorbed. So if our solution here appears blue, I'm sorry, if our solution is orange here, it will basically absorb light in the blue spectrum, which is why we set it at 470. So because we set it at 470, it's absorbing in the blue, which means when we look at the solution, it'll actually be the complementary color to it, which would be orange. If our solution looked red to us, we would set the wavelength probably in this greenish section. We had a purple solution, we would set the wavelength in the yellow sort of region. So again, the wavelength being absorbed is complementary to the color that we actually see of the solution. To figure out the energy, this is again basically our energy equation that we've seen before. H times C divided by the wavelength. Again, that's Planck's constant, which is H. That's the speed of light. And this is our wavelength that does need to be converted to meters. So there's 10 to the minus 9 nanometers. 10 to the minus 9 meters in a nanometer. So that's that conversion there. Gets us 4.23 times 10 to the minus 19 joules. This is really joules per atom. We're looking for kilojoules per mole. So atoms and moles kind of conversion tells us Avogadro's number here. Going to be involved. That's Avogadro's number. So multiplying by Avogadro's number will give us, and then obviously converting it to kilojoules, 255 kilojoules per mole. So when we do this part of the conversion, we will end up with joules per mole, and then just do 1,000 joules and a kilojoule to get us down to here. Any questions on that calculation? So that should be a very similar calculation to ones you've done before, probably last semester when you were dealing with wavelengths and those type of things. And again, that number represents the energy difference between the lower d orbitals and the higher d orbitals. Again, that number would represent how much energy difference there is between these d orbitals. So how do we know if we're going to get, basically a big sort of splitting that's going to occur or a small splitting that's going to occur? And it really does have to do with the ligands that are present. There are certain ligands that are referred to as strong field, and there's certain ligands that are referred to as weak field, as we see down here. What does strong field means? Well, strong field means that the separation here, if this was strong field, is going to be relatively big. And what that would mean is as these electrons would go in to populate this, they would go into always the lowest energy first, and then decide, well, these higher guys are way too far up there. We're going to just come through here. Let's say they had 5 electrons to distribute, and they would end up here. And again, in this case, what we would get is a lot more paired electrons. And that's what is sometimes referred to as a low spin complex. Now, if the opposite was true and we had our lower D1s here, which is our, XY, YZ, XZ, and up here, which is our squared guys. And we had this sort of splitting here that was weak field. What would happen if we wanted to distribute those same 5 electrons? They would go in one at a time and go, well, that's not too bad. We'll just go in like normal. And we get, again, a very different distribution of those electrons that are, again, coming from the metal. And this would be what we have a lot of unpaired electrons, which gives us what is referred to as a high spin complex, a lot more unpaired electrons. What we're talking about here, by the way, in terms of this splitting, is an octahedral arrangement and a coordination number of 6 in this particular case. So this is a coordination number 6 and the splitting that we see here. So kind of to the left here is our weak field, kind of to the right is our strong field. You may be wondering what's the deal in the middle. The deal in the middle is they a lot of times will give you some piece of information. They'll say, hey, do it for the strong field, or do it for the weak field, or do it as a low spin or high spin complex. And sometimes you may not be given any piece of information. And what that means is sometimes it doesn't make a difference, regardless if you did it sort of weak field or strong field, you'll end up with the same number of unpaired electrons. And that's a very common sort of question that's asked is, what is the number of unpaired electrons that you have in this sort of complex ion? Any questions on that there? All right, so let's take a look at one here, are these two here, and see what we got going on. So if we look at this Fe, F6 sort of guy, complex ion, first off, if we look at the iron here for Fe, F6, -3, this is -1, -6, this is +3. So the oxidation number of iron is +3. If we look at iron with no charge, it is argon 4s2 3d6. With a +3 charge, remember that they do lose the s electrons first. which is 2, and then we lose one more there, which means we would end up with 3d5. And those are the 5 electrons that we see here that are going to be needed to be distributed here. When we look at F as the ligand, we see F sort of in the middle, and we will kind of do it more sort of weak filled. So it's kind of hanging in the middle-ish. So it's a little bit more this way. So we'll do it for weak filled. And if we do it for weak filled, what that means is the splitting here is not going to be very big difference. So when the 5 electrons go in, they would go here first, here second, here third, and then actually go in like normal. And we end up with 5 unpaired electrons. And this definitely would be a high spin situation. Now, if we look at the same iron here, this is also +3 because this is -1. There's 6 of them. Now we have the same 5 electrons, but in this case, the ligand is Cn, which is definitely over here on strong field, which means the separation here is going to be large, right? And that means when the electrons come in, they'll go 1, 2, 3, then come back 4 and 5. We end up with 1 unpaired electron, giving us a low spin sort of complex. So, depending on the ligand that's present, we will get some different ones here that would occur. So why don't you try one here? Why don't you do it? Why don't you try this one here that we saw earlier, I think somewhere. You do cobalt Na3 6 with a +3. And since Na3, why don't you do it for more of a strong field? Let's see what you come up with. So draw the arrows, the boxes, and see what you come up with. How many unpaired electrons? So first off, we need to figure out what the charge is on the cobalt. So that's 0, which means obviously this needs to be +3. Looking at, again, cobalt with no charge, you're looking at argon 4s2, 3d7. Cobalt with a +3 charge means it lost 3 electrons. So that would be 2 from there and 1 from there, which would yield you 3d6. So we're really talking about 6 electrons that we need to distribute. We see here it is a coordination number of 6, which means it's going to be this octahedral arrangement where we get the splitting on the bottom of our 3d orbitals. And up on top are kind of squared over orbitals, if you will. So when we look at Na3, it is towards the right there on that list, more of a strong field, which means the separation here is going to be relatively big. So when we distribute those 6 electrons, 1, 2, 3, they're going to decide when they get to the end there that those upper guys are too high in energy. So we rather come this way first, and we would actually end up with 0 unpaired electrons in this case. Any questions on that there? Now, let's just say, for sake of argument, you did it as we did, the same cobalt, with, we'll do like, say we did cobalt with water here. And let's just say we'll do this as weak filled for that particular one. We would end up with the same 6 electrons. But if it was weak filled, it would go in like this and then go this way because it was weak here between these two. And we put 1 more here. We actually would end up with 4 unpaired electrons in this case. And definitely be more of a high spin versus a low spin guy. This would be high spin. question on sort of how to distribute those guys? Okay. So here's just your different arrangements that you could have for octahedral arrangement. Again, this is specifically talking about a coordination number of 6 and the splitting that occurs. And you can see on the left-hand side, that's all high spin, which means we have a weak field happening over here on the left. Over here is low spin, which means we have strong field happening, which again just basically means that energy difference between the lower and upper d orbitals is pretty big, that those electrons don't want to go kind of up there first. They rather kind of stay in that lower energy. Now, things are a little bit different when we get into some different coordination numbers. This is tetrahedral complex. This is now a coordination number of 4. And here we see the same splitting, except that it is sort of opposite of octahedral, so kind of opposite of our coordination number 6. Here we have our 3 d orbitals on higher energy, our 2 guys on lower energy, and it basically works the same way. Again, if you had a weak field, you know, it would come through and feel like normal and then go up. If it was strong field, it would go this way, then this way, and then up. So, you know, kind of works the same way, except that we have the different d orbitals on the bottom, and obviously those other ones up there on top. But again, works sort of the same way, depending on the splitting on the ligands that are attached and weak field, strong field as to how you would fill it up. Now with square planar, which is also coordination number of 4, we get a lot of different splitting happening here, these different orbitals. And again, they do feel kind of like normal. So if everything was sort of not big separation between these orbitals, they would just fill in like normal. If there was sort of a big split between them, they would fill the lowest ones first, then go to the next one, fill those, go to the next one, then fill those. So that is square planar, which is coordination number of 4. For us, you will not be responsible for this particular one, but you do need to know the tetrahedral splitting and how to distribute the electrons, and you do need to know the octahedral splitting and how to distribute the electrons. Any questions on any of that there? So you won't be responsible for the crazy looking one here. And that should wrap this chapter here.